Hello everyone. If you are seeing me and seeing this, it means that I am at home with a 6-month-old daughter who's not feeling very well today. Anyway, so I'm going to give you a little bit of heads up on the notes. I did include this PowerPoint. You can take a look at it on your own as you please. But I thought I'd talk you through a few things because it's a bit complicated on the first time out. So, on the graph itself, you're looking at temperature in Kelvin on the left-hand side, and then heat input along the bottom. So imagine you have a substance that starts out at ice and ends up as water vapor as the heat is added in, moving from point A and then on beyond point E. It is 1 gram of ice to begin and then converted to steam. The ice actually starts out as cold ice. You might not think about that, but ice can be colder than freezing. And so in this particular case, it's 243 Kelvin, and then you start pumping heat into it through some method, and the height, the ice, gets warmer and warmer, so it starts warming up. By the time it makes to point B, it's actually starting to melt. So at that point, it is going to go from ice to water. But from B to C, even though heat keeps being pumped into the system, it doesn't rise in temperature at all. In fact, all of that heat goes straight into breaking the bonds, which make up the crystalline structure of the ice. And so instead of raising the temperature or causing greater vibration in the substance itself, it just goes into taking those crystalline structures and ripping them apart. And so you end up with no temperature change whatsoever, and yet it stays flat and in the melting process. So that is pumping in additional heat. Turns out that that amount of temperature, that amount of energy that's placed into that system has a special name, and that special name is called the heat of fusion. So the heat of fusion is dependent upon every individual substance. Water itself, or H2O, has a particular heat of fusion, and gold has another one, and silver has another one. And each of those is what happens when you're in the process of melting. It does not raise the temperature when it's melting. That temperature, that heat goes straight into the process of the phase change, or the melting point. Once everything's melted, though, on the flip side, from C to D, you go into this process of the MC delta T. So the specific heat then factors in. You pump in energy, and it raises the temperature of the substance itself as it comes its way up. Once you hit D, though, you've now raised the temperature of that water all the way up to 100 degrees Celsius, or as you can see on the chart, the 323 Kelvin, approximately. And at that point, you are now hitting the vaporization of the water instead. And during that point, you pump in more and more energy, but the temperature remains the same. And at this point, you're now causing the phase change from liquid water into gas water, or steam. And that temperature stays the same during that time frame. However, what does happen is the energy has a name. That energy that you pump in to get the phase change is now called the heat of vaporization. So there's a certain amount of energy that goes into that. You can see it down below. Notice it's quite a lot, from 813.7 joules and then continuing rising on up to 3,073 joules is quite a lot of energy in order to do so. Once you get past E, then it heads back up again and creates warmer steam, so you can have warm steam versus cold steam. Turns out with solid, liquid, and gas, there's actually a different specific heat for each one of those sections. So that's a little bit complicated, but there they are. So there are different different specific heats of fusion and vaporization, as you can see for the different substances. So I have a very short list: copper, mercury, gold, iron, silver, lead, and water. You will notice that some of them are much higher than others. For instance, water itself has a much higher heat of fusion, as well as a pretty darn high heat of vaporization. Not the highest, but pretty high overall. So feel free to take a look at this. You'll need that information a little bit later. It's pretty easy to calculate the amount of heat that goes in to that melting process. You just need to know the amount of mass of the subject in the first place. So if you've got a certain mass of ice, for instance, ice that's going to be water, you can go ahead and take that mass and multiply it times the heat of fusion of water, and you'll find out the amount of energy that goes in order to melt that. Same thing goes true when it gets to steam. You just have to figure out the amount of water you have that you're changing into steam in terms of mass, multiply by that heat of vaporization, and you get the total amount of energy. So I've pointed out this a little bit here. We did this before. This is your specific heats dealing with a change in temperature. So this is during the parts of graph that are headed up at a diagonal versus the ones that are flat. So don't forget that. You'll need it today. Last but not least, I included a sample or an example problem here. That example problem is how much heat is needed to be added to raise 1 kilogram of ice at 0 degrees Celsius to water at 21 degrees Celsius. Keep that in mind. What would you need? If it's ice, you need to first do a phase change. So based on the fact that it's a kilogram, we need that. And I do include these two specific heats as well as the heats of fusion in terms of kilograms. So keep that in mind. And you'll notice that is true on this slide here. These are given in joules per kilogram. So the heat of fusion is in joules per kilogram. So first we need to change this ice into water, and then secondly, heat that water up to 21 degrees Celsius. So it's a two-step process, excuse me. You cannot combine them very easily, but you can do them one piece at a time, getting the amount of energy for each piece, and then just adding those two pieces together in the end to find out the total amount of heat. Today's work overall, after taking a look at that, is a handout based on a stove that I received years ago when I started backpacking. And there's a few questions that I have on it. You'll need that heat of fusion and the heat of vaporization for water in order to determine some things like how much energy does it take to bring 1 kilogram of snow to boil, and so on. So use the chart above in order to figure out how much heat can be supplied over a burn, maximum burn. So you need to figure out during that 60 minutes of maximum burn, which is here. The heat output itself is 10,000 BTUs, and you'll need to convert that into joules. So why did I put that in BTUs, which are British thermal units? The answer is that's what the REI website gave. So I went ahead and just copied it straight off the REI website, and then put some conversions in there so you have something to go from. So 10,000 BTUs needs to be converted into joules before you can do any work with it overall. So I wish you luck in order to make sense of this, work with each other, and try and come to the best understanding that you can. I will hopefully be in tomorrow. I should be in, not tomorrow, but the next day. Anyway, tomorrow is, I'm recording this on Monday night, so I'll be out Tuesday, but I should be back in Wednesday to help make sense of this overall. Anyway, good luck, and I will see you soon.